Hello students, welcome to JCE eConnect series of lectures. So in previous lectures we have solved some numerical problems on how to calculate the moment capacity for the given section, and in this particular lecture we'll see the design steps for a laterally supported beams that is I sections. So again there are two types here. For the type 1 already we have seen, that is a determination of design bending strength for a given beam section. So how the design bending strength for a given beam section can be calculated, we have seen in previous lectures. So just we'll recall back just step 1. So in step 1, from steel table, note down all the properties of the section given, such as height of the section, that is the depth of the section, width of the flange, thickness of the flange, thickness of web, then the root radius and this elastic section modulus. These all properties we get from the steel table. These all properties you have to note it down. Then for the plastic section modulus, that is ZP, plastic section modulus ZP, for that you have to refer IS 800 2007 annexer H, page number 138. So that page you refer for getting the ZP value. Then the next step you have to do is the classification of section. So for that you have to calculate the ratios, two ratios, that is one ratio is the for a flange element and the other ratio is for the web element, that is flange to thickness, then the web to thickness, then where the B represents the outstand of flange, that is half of the flange width, then the D represents the depth of the web. So this depth we have calculated is for the rolled section, and this depth is the effective depth for calculating the ratios. Then epsilon root of 250 by Fy, then one we get for Fy 250 Newton per millimeter square. Then you have to refer IS 800 2007 table number 2. So after getting the ratios, page number 18, you have to refer for a rolled section. So this is the table you can see in IS 800 2007. So the ratios up to 9.4 it represents the plastic section, and beyond 9.4 and up to 2.5 it represents the compact section, and beyond 10.5 and up to 15.7 it represents the semi-compact. This is for the flange element. And for the web element, up to 84 epsilon is a plastic, and 84 to 105 is a compact, and beyond 105 and up to 126 epsilon is semi-compact. Then for example, if suppose the ratio of flange element is less than 9.4, since epsilon is 1, and if the for the web element the ratio is less than 84, then the section is classified as plastic section. And also one more check you need to do, if the ratio of web element, that is D by TW, is less than 67, check for web buckling is not required. If it is beyond 67, then you have to go for the check for web buckling. So once you come to know in what classification the section is lying, based on that you have to calculate the design bending strength MD. So again, in calculation of design bending strength MD, we know there are two cases when the factored shear force is less than the design shear 60% of the design shear strength. That is the case of low shear. Then for that one, MD is a beta B ZP into Fy by gamma mu, and this should be less than 1.2 ZE into Fy by gamma mu for simply supported beam. And for a cantilever beam, this MD should be less than or equal to 1.5 times ZE into Fy by gamma mu. So okay, Then after this one, again the next will be what? Check for shear. So once, that is for the low shear, once we check, we have got the low shear case, then check for shear you have to do, that is V equal to WL by 2 for a simply supported beam carrying UDL, and V equal to WL for a cantilever beam carrying UDL. It is simply supported beam. This is simply supported beam carrying UDL. These are the support and UDL of W. Then this is the span of L. This will be WL by 2. This side is WL by 2. Similarly for cantilever, this is the cantilever carrying UDL W, and the reaction will be WL here. Okay. So this is WL for cantilever beam carrying UDL. Then you have to calculate design shear strength. This is the formula you have to use, where AV is the shear area, that is H into TW into Fi divided by root 3 gamma MO. Then after that you have to consider one more case, when factored shear force is greater than 60% of VD, which represent the high shear case. Okay, then the design bending strength can be calculated by using this one, MD minus beta into bracket, it will be MD minus MFT, which should be less than or equal to 1.2 ZE into Fi by gamma MO, where beta can be calculated into bracket 2 times of V by VD minus 1 whole square. And for a semi-compact section, if the section is lying in semi-compact classification, then MD can be calculated by using this formula, MD equal to ZE into Fi by gamma MO. Then next, in step number 5, if factor load to be calculated of given span is L, then maximum bending moment you would need to calculate, that M equal to WL square by 8 for a simply supported beam carrying UDL, and M equal to WL square by 2 for a cantilever beam carrying UDL. Then after calculating bending moment, equating the design moment to maximum bending moment, then M equal to MD, then MD is equal to WL square by 8 for simply supported beam. From this we get the load carrying, that is load 8 into MD divided by L square for simply supported beam, and MD equal to W square by 2, so we get W equal to 2 MD divided by L square for cantilever B. Okay, so this we have seen previously, we have solved the problem on these steps. Next type is very important type. The next type is next type is, it's a very important. Design a beam for a given loading condition. So the load will be given, for that you have to design the beam. So the steps here, you need to follow. Step number 1, note down the material properties first. You have to note down the material properties and partial safety factors. Material properties, then partial safety factors, then the yield stress you need to, then the yield stress of web material, then the partial safety factor for material, then the partial safety factor for the load. Then next, second step you need to do is a load calculation. You have to calculate the load, and that is a dead load and live load both. Then the assumed self weight of the beam is generally the self weight of the beam to be assumed between 0.8 to 1 kilonewton per meter if not given self weight. Then add dead load and live load to self weight. So this is self weight, then add dead load and live load to self weight to obtain the total UDL. Then make it factor. After calculating total UDL, you have to total factor load you need to calculate, that is total UDL multiplied by the factor of safety. So factor of safety to be taken is 1.5. Okay, then suppose if room dimensions with spacing of beams given, then the total UDL to be calculated, the room dimensions with spacing of beams given, like this. If the room dimensions like this, L into B, then the spacing of beams are given like this, then the total UDL to be calculated, dead load plus live load into spacing of beams plus self weight of a beam for intermediate beam and half of the total load for end beams. So dead load plus live load plus spacing into spacing of beams plus self weight of the beam for intermediate beam and half of total load for end beams. Okay, so this you can understand while solving the numerical problem. Okay, so this is the step number 2. Then the step number 3. So in step number 3 you have to do calculate the maximum bending moment. So calculate m equal to WL square by 8 if simply supported beam is given. So for simply supported beam, the maximum bending moment is WL square by 8. If suppose cantilever beam is given, if you are designing a cantilever beam, then you have to take for maximum bending moment WL square by 2. Then in step number 4, required plastic section modulus. So here how much plastic section modulus is required to calculate by using this formula, because you know the bending moment, then partial safety factor, then Fi, calculate the required plastic section modulus. Okay, then after calculating the required plastic section modulus, then the selection of section. So you have to select the section, means you have to you refer IS 800 2007 table number 46 page number 138. So for this required plastic section modulus, you have to select the section. Select I section having a plastic section modulus more than required. So whatever the section ZP you have calculated here required. So for this one you have to select a section which should have more than the required ZP. Okay, and note down the properties of section, whatever the section you choose. And for that section you have to note down the properties like depth of the section, width of the flange, thickness of the flange, thickness of web and elastic section modulus and ZP section modulus. And from the steel table you have to take root radius R1 and IZZ, and preferably you have to select ISLB, ISMB or ISWB. For the beam section, preferably these sections are to be preferred. Okay, so I'll repeat, you have to calculate the section modulus required. For this required section modulus, you have to refer IS 800 2007 tables 46 page number 138, where you will get the various section, you will get various sections, and for that section you will be having a various section modulus. Then the select I section having a section modulus more than the required. Then note down the properties of the section. Then after getting or after selecting the section, you have to do the classification of beam section. So you know how to do the classification of beam section, means whether the selected section is compact or a plastic or a semi-compact. You have to decide based on the flange element ratios and the web element ratios. Calculate for that epsilon and the ratios of flange element, ratios of web element. Then from table number 2 of IS 800 2007, classify section as plastic, compact and semi-compact. Means based on these ratios and the limits given for these ratios in table number 2 of IS 800 2007, do the classification of section, whether the section is plastic, compact or semi-compact. Then after this one, once you classified the section, then accordingly select a value of beta and formula for calculating design strength of the section selected, which should be more than the maximum bending moment and shear force developed in a beam section due to load. Okay, so whatever the section you classify, based on that one you have to choose the value of beta and formula for calculating the design strength of the section selected, which should be more than the maximum bending moment and shear force developed in a beam section due to load. Then in step number 6, the trial section is checked for the shear. Whatever the section you have chosen, that is the trial section. You have to check here, it has to pass in all the checks. You have to check for the shear, and for that one you have to calculate the design shear strength, that is AV into Fi, where AV is the the shear area, that H into TW divided by root 3 gamma MO, which should be more than the factored shear force, then it is okay. Then if suppose the factored shear force whatever you obtained, if it is less than or equal to 60% of design shear strength, then this is the case of low shear. And if suppose if you are getting the factored shear force is more than 60% of VD, it is the case of high shear. Accordingly, you have to apply the moment capacity formula to calculate the design bending strength. Then the trial section is checked for design bending strength after calculating the shear based on the whether it is a low shear or the high shear. Based on that, you have to check for the design bending strength. Accordingly, IS 800 2007 page number 53 you have to refer. Then for the shear case, the design bending strength should be more than the moment obtained. Then MD should be less than or equal to 1.2 JD into Fy by gamma MO. This is for the simply supported beam. If suppose cantilever beam is given, it should be less than or equal to 1.5 times of JD into Fy divided by gamma MO. For high shear case, this design bending strength should be more than MD. And MD and MDV calculation, and how to calculate MD and MDV, then just you have to refer previously explained regarding the MDV, or you can refer page number 53 and 70 of IS 800 2007. Then after this one, the next is what? Trial section checked for the deflection. This trial section you have to check for the deflection. For maximum deflections, so maximum deflection delta max 5 by 384 WL raised to 4 by EI for a simply supported beam carrying UDL. This is just for one beam, just simply supported beam carrying UDL. And similarly for other conditions, delta max, if you want to, for other conditions, just I have taken one condition. For other conditions, see in this one, I'm referring here, this one, maximum shear force, bending moment and deflection for standard cases. See here given type of beam and loading. If cantilever beam with a concentrated load at the free end, if suppose cantilever beam you are using and the load is being acting over the cantilever beam at one of the end is a concentrated load, and maximum bending moment, you know, the M equal to WL, and maximum shear force V to be taken as W, and maximum deflection for a concentrated load delta max will be WL cube by 3I. So you have to remember these all cases when you are designing a beam. You have to know all the cases. So depending upon the case given in the problem, if the cantilever beam with concentrated load is given, then you have to take this is a maximum deflection formula. And if cantilever beam subjecting to UDL is given, this is second case, cantilever beam subjecting to UDL like this, F span L, then the maximum bending moment is M equal to WL square by 2, and if shear force at support will be V equal to W into L, and maximum deflection will be WL raised to 4 by 8 EI. Okay, so this is the deflection. Then if suppose in the problem given simply supported beam with concentrated load at the mid span, simply supported beam with concentrated load at the mid span is given, then a maximum bending moment, that is M equal to WL by 4, then the shear force V equal to W by 2, and delta max will be WL cube by 48 EI. This is for concentrated load acting on simply supported beam at mid span. This is the delta max deflection. And suppose if simply supported beam carrying uniformly distributed load for entire span like this, UDL is acting, UDL acting over a simply supported beam, then bending moment, you know how to calculate bending moment. The bending moment can be calculated M equal to WL square by 8, and the shear force V equal to WL by 2, and deflection delta max will be 5 by 384 WL raised to 4 by EI. So you have to remember different cases, and these all cases you have studied in structural analysis or strength of material, how to get the bending moment for a simply supported beam or a cantilever beam subjecting to concentrated load or the UDL. You know how to calculate bending moment as well as the shear force, and also maximum deflection for different cases, and where the W is the point load and U small w is the uniformly distributed load, and L is the span, I is the moment of inertia, and E is the Young's modulus, and note down EI will be the flexural rigidity. You have to remember these all cases while designing the beam. Depending on the cases given, you have to design. So in this one, just I have taken one simply supported beam. The delta max can be calculated 5 by 380 per WL raised to 4 by A for a simply supported beam carrying load. So similarly for other conditions, so you can refer different conditions, delta max. Okay, then the permissible deflection, as per the code, that is a table number 6 of page number 31, table number 6 of page number 31, right here, table, here it is written, table, you have to write delta equal to L by 300. This is for simply supported beam, permissible deflection, and delta equal to L by 150 for cantilever beam. Refer IS 800 2007, table number 6 of page number 31. If delta max is less than delta max is less than delta, section is safe against deflection. If you are getting maximum deflection according to the code, this is a permissible. If delta max is less than delta, then the section is safe against deflection. Then next you have to do the check for web buckling. Assume stiff bearing length. Generally the minimum stick bearing length to be assumed is 100 mm, and the bearing strength for that one, B1 plus N2 into TW divided by TW into Fy by gamma MO, where N2 to be taken 2.5 times TF plus R1. As you know, this is the I section. If suppose this is the stiff bearing strength, this much is the B1, or you can say it is a B1, and the load dispersion under the support, the load get dispersed at a ratio of 1 is to 2.5. 1 is to 2.5. As you know, it is I have explained this one in a web crippling, and this will be what, TF plus R1. Okay, so how to get this N2 is 2.5 TF1? So here this ratio is given for 2.5 horizontal, 1 is vertical. Okay, and up to here, if I take this as a N2, for N2 horizontal, the vertical is what, TF plus R1. Then cross multiply this one, you get N2 into 1 is equal to 2.5 TF plus R1. Then N2 will be 2.5 TF plus R1. So this one. Okay. So this is the load dispersion generally we take for the bearing strength under the support condition. This is B1 stiff bearing is given. Then the N2 to be calculated based on the load dispersion at a slope of 1 is to 2.5. For 2.5 horizontal, 1 is vertical. Means for every 2.5 horizontal load dispersion, the 1 should be the vertical, like that. If N2 to be taken up to here, then for N2 horizontal, the vertical will be TF plus R1. TF plus R1. Then cross multiply it, you will get N2 equal to 2.5 into bracket TF plus R1. Okay. So these are the steps you need to follow for the design of beam for the given loading condition. For the given loading condition, so the load will be given. So very important, type 2 design a beam for a given loading condition. Okay, so many a times this type of problem will be asked in an exam for 15 to 20 marks directly. 15 to 20 marks. Okay, I hope you understood these steps. So in next lecture, So we'll take one design problem and we'll follow these all steps. Thank you.